All right, well, good afternoon and welcome. So this is the replica of the Fat Man. This was dropped in Nagasaki. So today, um, all these countries have nuclear inventories. You can see, Russia 4,000 plus, United States almost 4,000, United Kingdom 200, even North Korea has about 60, Israel 90 to 100. Anyway, everybody has one, so why not you? And so let's go and build a bomb. First question is, what kind of bomb? What is this? What type of bomb? Do you want a fission bomb, an atomic fission, or a thermonuclear, a fusion bomb? Well, there's a big difference. The atomic bombs, they split heavy atoms like uranium and plutonium, and they create a kiloton range explosion. A kiloton is 1,000 tons of TNT. That's a hell of a lot big bang, but anyway, it's the kiloton range. On the other hand, thermonuclear weapons or hydrogen bombs, they fuse light atoms like hydrogen isotopes, and they produce megaton range yields, million tons of TNT. So the nuclear fission is a reaction in which the nucleus of an atom splits into two or more nuclei, and in the process, they release a lot of energy and also neutrons. And here is a picture of it. I forgot to bring my pointer. I wanted to point something. I forgot. Anyway, you notice that there is an incident neutron that is necessary. So when a neutron hits a fissionable nucleus, that nucleus gets discombobulated and eventually splits into two parts or more parts, but usually two parts. And those are the fission products, and they also produce additional neutrons. Now, these additional neutrons then find more nuclei, fissionable nuclei, and they fission, and so that produces then the chain reaction. On the other hand, the fusion is totally different. They're very small atoms, like deuterium and tritium, and I'll get into that in a minute. They fuse, and by fusing, they disperse a lot of energy and also neutrons. Now, let me just point out that hydrogen is the smallest atom there is. It consists of one proton, that's it. And in the normal state, and an electron around it, but one proton in the nucleus. There are hydrogens that have an additional neutron in it, and that is an isotope of hydrogen. That's called deuterium. That's the one on the upper left. And if it has two neutrons in the nucleus and one proton indicates that it's still a hydrogen, then that is a tritium atom. Anyway, so this is the fusion as opposed to fission. But let's go to fission, because we're going to start with fission. The fission requires, as you can see on the left, a fissionable nucleus. Now, there are very, very few fissionable nuclei on Earth, in nature. In fact, there is only one good one, that is uranium-235. There are other nuclei that are fissionable, but you have to make them, like plutonium-239. You have to make plutonium-239 because it exists in nature, but in traces, and it's not enough to do anything with it. So, Yeah, so this is what I just said, that uranium is the only one really naturally occurring fissionable nuclei. And the best artificial is 239. There are other artificial fissionable nuclei, but this one is the best for a number of reasons. All right, so let's try first uranium. Let's make a uranium bomb. Okay, the uranium bomb is the one that was dropped in Hiroshima in 45. So okay, so you have the neutron. The neutron hits a nucleus of 235. You have the atom 235, the 235. That one splits into two parts, usually two parts. And in this case, I put down the examples of barium and krypton, but it can be other fission products. It releases a lot of energy and it releases additional neutrons, which will go on to produce more fissions. The same thing happens if you use plutonium-239. There is the incident proton, there is the fissionable nucleus. The fissionable nucleus separates into two parts or more. In this case, the example is xenon and zirconium, and additional neutrons. But let's go back to uranium because that's the one that we're going to work with. So what do we need to make a bomb with uranium-235? Well, we need uranium-235, but we need it in the metallic form. And we need a lot of it. And so a lot of it, what does that mean? Well, the bomb used in Hiroshima weighed 141 pounds. And so, if we're going to make something like this, there will be losses in the process. So let's say 200 pounds. Okay, so we need 200 pounds of a metallic uranium-235. So how do you get it? Well, it turns out that this is natural. It exists naturally in uranium mines. And these uranium mines exist in a number of places in the world. Even the United States has uranium mines. They're not very big. They're not very good in the purity of uranium, but they exist. The best ones are in Canada. And so the ore is called pitchblende or pitchblende, and it contains from 0.1% to 20% uranium oxide. Okay, not uranium metal, uranium oxide. And the Canadian ores go up to 20%. They're pretty good ores. So anyway, so you have a pitchblende, they take it out of the mine, and they crush it and put it in a huge vats of sulfuric acid. And the sulfuric acid extracts the uranium from the ore, and it forms yellowcake. And yellowcake has an enrichment of up to 70 to 90% of uranium oxides. And I calculated out that it costs today about $85 a pound. All right, so no, we can get the yellow cake. We can buy it.
Where do you buy it?
Where do you buy it? Well, there are.
Costco?
I haven't
Haven't found
where to, but you can buy it in the market.
In the open market?
In the market, in the open market.
Wow.
Not in Orlando, but you can buy it. But there is a problem with it. And so we have yellow cake, but the uranium that's in it, it's all of the uranium forms. You see, uranium has various isotopes, which means that the nuclei of uraniums have different neutrons. And let me show you what I mean. And so I don't have my pointer, unfortunately. So these are the isotopes of uranium. U-32, 33, 34, 35, 36, 38. Now, there is the second column there that I would like to explain, half-life. All these elements are radioactive and they decompose. They emit alpha particles. And half-life refers to the amount of material that is left after the half-life. So the first one, the 72 years of half-life, it means that if you have a pound of uranium-232, 72 years later, you'll have half a pound. And 72 years after that, you'll have a quarter pound. That's what half-life means. So look at the half-life of uranium-238. Is 4.5 billion years. I mean, that's a pretty long half-life, which means that when Earth was formed 4.5 billion years ago, we have twice as many uranium atoms or twice as much uranium as we have today. But we still have plenty.
Is there a reason why the half-life is so different?
That is a characteristic of the nuclei. So different nuclei, they have different characteristics. One of them is half-life. And I don't know if anybody knows why that is so, why the number. So, but this is what it is. But look at the third column, and that's a very important column because it shows that most of the ore, most of the uranium in the ore is 238. Now, what we need is 235. And we only have 0.72% of uranium is uranium-235. So we need a hell of a lot of uranium, a hell of a lot of yellow cake in order to obtain our 200 pounds of uranium-235. So I've made a little calculation here. How do you do that? Well, how much yellow cake do we need? Well, we want 200 pounds of uranium-235 metal. So that means that we have to correct for the purity of the oxide in the yellow cake. Remember that I put 7 to 90%, I put 70%. We have to correct for the natural abundance of uranium-235. There is only 0.72% of all the uranium in it is 235, and we have to correct for the formula. You see, what is in the yellow cake is uranium oxide. That means uranium and oxygen. So if you only calculate the uranium, which is what we need, you have to correct it and you divide it by 0.85. So in total, you make that calculation, we need 47,000 pounds of yellow cake in order to get 200 pounds of uranium-235. And, open up your checkbooks, that means $4 million roughly in today's cost. Okay, so now we bought the yellow cake, we paid the $4 million. And so what do we do with it? Well, it's a kind of a long process, so let me show you. So you bought the yellow cake, there it is. Now you have to treat it in many chemical ways. I'm not going to go into the details of this, but you treat it with nitric acid, you treat it with something else to extract it. You treat it with ammonium hydroxide, you calcinate it, you burn it, you reduce it with hydrogen. Finally, you get down to that red box, uranium oxide. Uranium oxide. Okay, so that uranium oxide has the uranium in it is 0.72% of the total uranium that is in there. So we have to separate it. We have to separate the U-235 from the U-238. How do you do that? Well, you have to convert it into a gas. And the gas is uranium fluoride, UF6. And the way to do it is by two steps. There's a hydrofluorination with hydrofluoric acid, and then with a fluorination with fluorine. So eventually you get your UF6, which is a gas. And now we can separate the 235 from the 238. How do you do that? Well, with what's the name? Centrifugation. So you centrifuge. So you send in the gas, you see the supply, UF6 supply, you send it in, these things rotate very fast. And the heavier uranium goes to the extremes, and the lighter uranium, the 235, stays in the middle. And so you pump up from the middle the uranium 235, which is enriched. And so you keep doing that for a zillion times and with a zillion centrifuges. And these are the famous centrifuges that everybody talks about when they talk about making, the material for the uranium of the bomb. So you have thousands of these centrifuges, and they work a long, long time because it's a very, very slow process. But hey, eventually you do get your enriched uranium 235. And the longer you go with it, the richer it is. You can go, and the Iranians are up to 60% now. But in order to get a bomb grade uranium 235, you need 90% or better. 90% or better. Maybe you can detonate it with 88%, but it's not good. 90% or better. So, okay, you have your UF6, you have 235 now. This is uranium fluoride 235. Now you reduce it. You chemically you form several salts, and eventually, and I'm not going to go to the details of that, you get to uranium oxide, which is on the left. Okay, it's a black powder, and you can do anything with it. But anyway, this is the material that you get after treating the gaseous uranium fluoride. But that's not good. What we need is metal. All right, so you again have to go to chemistry, and with a very high temperature and very high pressure reactions, you can reduce it to the metal. And there it is, a sample, U235 metal. That's what we need. But we cannot make this in any size. You have to, in fact, make it in relatively smaller sizes, because otherwise it will blow up. It will explode. All right, so why? Why is that? Okay, because there is such a thing as a critical mass. And uranium 235 has a critical mass, which means that above the critical mass, above a certain size, it will explode. And below that critical size, it will not. Why? Well, it's simple. Take a look at the left-hand side, the subcritical mass. The way that the bomb works is that you get a neutron hitting a nucleus, and that nucleus will separate and emit more nuclei, more neutrons. Those other neutrons will hit other nuclei, and that is how the chain reaction progresses. Now, if the mass is too small, too many of these neutrons will escape the mass, will escape and will not be used to do the fission. And so it will not explode. The one in the middle is the critical mass, which means that the number of neutrons that leave the sphere is the same as the number of neutrons that stay inside to cause more fission. And supercritical, that is what we want eventually, is when the nuclei stay in the mass and are used to split more nuclei and produce more fission. So this is why we cannot have a piece of uranium metal 235 larger than, say, the size of a softball.
Oh.
Because it will blow up. So you have to make it then smaller. All right. So how do you blow this up then? Finally, how do you make a bomb? That's very simple. Like that. You see, you cut it in two pieces in one way or another. So you cut out the middle of a sphere and you put it on the left-hand side of this gun barrel. And you shoot it. You see there is the explosive, the green material is explosive. You shoot it into the other piece, and when the two are together, they're supercritical and they explode. So that is how the Hiroshima bomb worked. They had a piece away from another piece. They're both subcritical, but when they met, then it became supercritical and it exploded. But there is one more detail. In order for the explosion, in order for the fission process to start, you need an electron. Remember at the beginning I showed it, you need the electron. So how do you start the electron flow? Well, with that little radioactive neutron, yes, the radioactive neutron source. Now, what is that? Well, okay, that is called an urchin. And it's about smaller than a ping pong ball. And what it has beryllium. Beryllium, the blue is beryllium, the one in the middle is beryllium, and the outside is beryllium. And the beryllium is separated from the band of yellow that you see there, which is polonium 2010. And so the idea here is that when the explosion occurs, when the small piece is shot into the other piece, this sphere will smash, and this will collapse. The protection of nickel and gold around polonium will get destroyed, and then the polonium, which emits alpha particles, will react with beryllium, which is the blue part, and produce carbon-12 and a neutron. Anyway, let me just go over this because it may sound a little bit complicated. In fact, let me go close here. So this is beryllium, and the middle is beryllium. This here is polonium. Now, polonium is a radioactive material, and it always emits an alpha particle, which is a helium-4. And it is separated by this nickel and this nickel gold material, because we don't want a premature use of neutrons. We want to reserve the production of neutrons for when the bomb is actually going to explode. And so that's when the bullet piece is sent into the other piece in the bomb, this thing is in the way, and this thing gets smashed. And that's how that nuclear reaction, those two nuclear reactions start and neutrons are produced. So that is why you need the urchin in every single one of these bombs. Hey, it's not difficult to get. Polonium is not cheap. You can get polonium. Beryllium is cheap. So we can get, and we can make urchins in our kitchen or barrage or something maybe. And so, okay, so now we have the bomb. And the little boy, that's the one thrown in Hiroshima, that had all of these components. And let me show you the inside of it. Let me just go here. And so here is the part of the uranium-235. And here is the other part that is going to go and envelope it. When the cordite powder bags, the yellow, that explodes. This piece will be sent into this one and will form a a supercritical mass, and then it explodes. So there it is. You know, it's not so complicated.
And so where's the
Where's the
urchin in
urchin?
that?
The urchin, yes, the urchin is here. The polonium beryllium initiator is here.
Okay, right.
Somewhere here, I don't know exactly, okay? But that gets crunched with the impact of the bullet, okay? Actually, you know, it's the other way around, because this envelopes cause an envelope, and it is there, so it hits, you see, when this thing reaches the bottom, it crunches the urchins.
So you end up with an extra neutron.
Yes, the urchin, when it's crushed, emits neutrons, and that starts the whole process. All this is almost instantaneous.
Yeah,
It is a very, very, very fast reaction. So, but this is how you do it.
So then the question is, if the neutron keeps the reaction going, how does it finally stop?
Well, because the bomb
Run out of
explodes,
material.
the bomb explodes, and everything separates.
Okay.
Yes.
Did they start? Did Einstein start on this in the 20s, whatever?
Einstein had nothing to do with this.
No,
In
who's
fact, he wasn't very happy with it.
It's Oppenheimer.
was it?
Oppenheimer.
Oppenheimer?
Oppenheimer,
And,
yes. Yes.
He managed.
The problem with this type of bomb, and particularly with the Hiroshima bomb, it is very inefficient. The truth is that only about less than 2% of the fissionable material actually fissioned. And so even then, it produced a hell of a big bang, but it's not a very good bomb. Yes.
When I was in Hiroshima, they said that unknown to me, when I think of a bomb, I think it hits the ground and blows everything up. They said that the bomb actually explodes in the air and then and destroys everything underneath it, and that so my question is, have I been contaminated by half-life?
You lost your hair.
The contaminants of the Hiroshima bomb were washed out by rain, by physically getting rid of it. So when you and I myself went to visit Hiroshima, we went there and there was no trace of radioactivity there. So don't worry.
Excuse me, question?
Yes, sir.
Why would it not work to take two subcritical spheres and shoot one at the other?
It would.
Okay,
Two halves, let's say you have a sphere and you have it, or half spheres. You put the half spheres together and you form a critical mass, it will go up, yes. That's another, the form in which you do it is very irrelevant, really.
it probably isn't as instantaneous.
It's
That's
probably,
the
well,
explosive
no,
method.
it probably is, yeah. But anyway, it's inefficient, it's not very efficient. A lot more efficient is the other one, the implosion type nuclear bomb. Because, well, we'll go into it and see why it is more efficient. But the implosion type is with the plutonium. Okay. So this again is the reaction, the nuclear fission process. You get the incident neutron. The neutron activates the nucleus. It separates. It forms the portions and the fission products and neutrons. But you need plutonium-239, and it's not available in nature. So you have to make it. And well, today we can make it. Even back in 1945, in fact 1941, they can make it. So how do you make it? Well, you need a nuclear reactor. Well, like that. Nuclear reactors are really sources of neutrons. So all the nuclear reactors you have, they're sources of neutrons. And so what really happens, the science of it, is that you have your uranium-238, that's how you start. And you have plenty of that because that's most of the yellow cake, and that would be relatively cheap. So you start with 238, you put it in the nuclear reactor, there's a neutron hits it, that forms uranium-239. Now, uranium-239 is also radioactive, but it emits a beta. It's not there are three types of radioactivity: alpha, beta, gamma. Alphas are helium nuclei, and you saw that how it worked with uranium-235. The emission of beta is an electron. Very simple, an electron. Gamma is electromagnetic waves. So anyway, U-239 emits a beta, and it forms neptunium-239. And it has a half-life for 23 minutes. So this is pretty fast. At the moment that it gets formed, it pretty soon becomes destroyed, and it forms a neptunium-239. Neptunium-239 also emits a beta, an electron, and the half-life is 2.3 days. So in 2.3 days, half of the neptunium will be transformed into our product. This is what we want, 239. So all you have to do, really all you have to do is take uranium-238, go to the nuclear reactor, put it in, and wait. And you wait about 3 months, and voila, you have plutonium-239. Well, I wish it was that simple.
Yeah.
So this is the inside of a nuclear reactor. So what you do to make plutonium-239 is that you use uranium oxide and you put it inside the reactor. And the uranium-238 will also have a 0.72% of 235. And those are the neutrons that feed the whole process. So with those neutrons, you'll see that you saw the reactions of how you convert it into plutonium-239. Anyway, so you have these bars, and you have hundreds of these bars, maybe thousands. And then you also have these black bars, and those are sort of regulators. If you have too much neutron emission, it's not so good. And so by lowering those control rods, you can control the amount of neutrons that happen to this world around. Those bars are made of carbon or some other material that absorb neutrons. That's how you control the nuclear reactor. So anyways, so that you put it in, wait for it a couple of months, and then you take out the raw material. Of course, the raw material now is a mixture of all sorts of stuff. It's a mixture of plutonium-239, but there is some uranium-238 left. There's a little bit of uranium-235. There's all sorts of other products. So you have to separate all of this. And all of this is done chemically. And I'm not going to go into the details, but you start with the spent nuclear fuel, and you treat it with the nitric acid, and you treat it with kerosene, and then you treat it with water, and then you treat it with this and with that and the other thing. And eventually you get to plutonium dioxide on the lower right, plutonium dioxide. That is your almost final product, because what we need is plutonium metal. Okay, that's what we need. But this is plutonium dioxide, which is the 239 pure. We don't have any other isotopes mixed in with this. And the reason we leave it at this stage for a while is because the metal, the plutonium metal, corrodes too fast. And so it's preferable to leave it in the oxide form and make the transformation, the reduction to metal when it's needed. So you have the plutonium 239. The price of this, I kind of looked it up, is about 11,000 per gram of plutonium metal. Okay, so again, get out your checkbooks. That will be for the 20 pounds that we will need. Is about $9 million. I didn't say this, but how much plutonium 239 do we need? Remember that we needed 200 pounds of uranium 235. With plutonium, we only need about 15, 20 pounds. Okay. We can make a bomb with 20 pounds of plutonium. That is one of the big advantages also, because it doesn't weigh that much of the plutonium bombs. So anyways, but the thing is that plutonium-235 does not have a critical mass. In other words, it's always subcritical. You can make it as big as you want, it will never explode. So how do we do it? How do we make this thing explode? Well, we have to compress it, make it more dense, to make it supercritical. And the way to do that is by compression. So it's been calculated that 2.5 compression, 2.5 times the compression of plutonium will raise the density enough to cause it to reach criticality. So what do? Well, we design an explosive lens. We put explosives around this ball of 20 pounds and compress it 2.5 times. And it has to be precise. I mean, it has to be compressed all over the surface, and it has to be at the same time. It looks like this, more or less. The explosive lens all around the plutonium metal. And in the real life, it looks like on the right. And everything below, underneath that, between these wires and the center, which is a small ball, all that is explosive. And it has to be, again, it has to be precisely at the same time. All of the explosives all around it will have to explode at the same time.
Excuse me, you mentioned that it has, the plutonium metal has kind of a best buy, it expires. So you can't
No, it doesn't expire, it oxidizes. The
oxidize,
surface oxidizes.
okay,
It rusts.
but it's still usable. In other words,
Well,
the plutonium bomb,
yeah, it's
doesn't
the
have to be
oxidation
used
is
quickly.
like it would be with a piece of iron metal. You take a ball of iron metal, you put it out there, and eventually you see that it's reddish on the surface. The same thing with the plutonium.
but it wouldn't give the bomb a shelf life, so to speak.
Oh, no,
Okay.
no, not nearly, no. So anyway, this is Fat Man. This is the bomb that was dropped in Nagasaki.
Oh.
And what it has inside is very simple. This is the initiator, okay, the neutron initiator, the urchin. It's very small. The thing is about that big. The rest of it is the ball of plutonium-239, which will be about the size of a not base, but a little bigger softball, about a softball. And the rest of it is explosives. And of course, these are the detonators. And they're all over the surface. And again, it has to be very, very, very precise. But man, they made it work in 1945.
So that explains the two different shapes of the two different bombs.
Yes, well, one was fat and the other one was long because of the shape of
Because of the type of,
the type of bomb, yes. So this is a lot more efficient than the uranium-235 bomb, but it's still, kilotons. And so that's nothing. That's small potatoes. Let's do the real bomb. Let's make a fusion bomb. Now those are the real ones. So anyway, a fusion bomb, as we talked before, refers to the fusion of two small nuclei. Now in this example, what I have, what happens in the middle of the sun, the interior of the sun. Two hydrogen nuclei, okay, fuse together, and it emits a lot of energy. That's why the sun is so bright, and that's why it gives us so much heat. And it produces all sorts of stuff. The problem, of course, is that protons have both positive charges. And in order to get them to fuse, you need a lot of energy to push them together. Now the sun has that much energy, and it is converted into 100 million degrees centigrade. That's what you need in order to fuse these two small nuclei. So we have to figure out how to do that. But anyway, let's just go on a little bit with how this works. Not only hydrogen nuclei, of course, but small nuclei will work. And for example, hydrogen and deuterium, you can fuse those two. Now, it's interesting to point out that if you hide the nucleus with a neutron, then the requirement of energy to fuse them together is a little bit less. So that's an advantage for using different isotopes instead of pure hydrogen. For example, deuterium and tritium. Now, in deuterium and tritium, you can see that the deuterium has one neutron, tritium has two neutrons in the same nucleus. And so they sort of hide the proton a little bit, so you require a little bit less energy to fuse these together. But they still produce a hell of a lot of energy. Okay, they produce a lot of energy. In fact, a lot more than the fission process. But they had studied which combination of these small nuclei is best for a hydrogen bomb. And so here we are. This is some of the data. So in the first line there, and you have a deuteron and a deuterium and a deuterium fusing together to make a helium-3 nucleus and a neutron. That process, in fact, that process has been used. The first hydrogen bomb exploded in the United States used that material. And it produces 3.27 million electron volts. MeV, a million electron volts, is a measure of energy. Okay, let's not go into the details, it's just a measure of energy. But you can tell that the next line, is the same two nuclei, but it gives a different process. Instead of a neutron, it produces two hydrogens, a tritium and a hydrogen, and it gives off 4 MeV of energy. But look at the third line. The third line is a deuterium nucleus plus a tritium nucleus, which forms a helium nucleus and gives off a hell of a lot more energy. So hey, that's a better candidate. Okay. The other one, the last line, is a deuterium nucleus with a helium-3 nucleus, which also produces a helium-4 and a hydrogen. And that gives off even more energy. The problem with that is that it's sort of tricky to make the helium-3 material. It's just complicated to make it. So the best candidate here is to use deuterium and tritium to make the explosive. So let's do that. Deuterium is naturally occurring. There is a certain percentage of deuterium in the water, in all water, in all oceans, in all rivers and lakes. So you can extract it from there, and it's relatively cheap. Here it is, you extract it from using isotope separation method. It's cost $1,200 a pound compared to millions before that we talked about. The deuterium is cheap. Now, tritium is something else. Tritium is radioactive. Deuterium is not. And it has a half-life of 12 years, but the way to make tritium is in a fusion reactor, and it's really complicated. It's complicated, it's dangerous, and it's expensive. But chemists have found a way, and an alternative is that tritium can be produced from lithium-6 by irradiating it with neutrons. It's one of these nuclear reactions. Lithium, the naturally occurring lithium, consists of two isotopes, lithium-6 and lithium-7. Lithium-6 is 7.5% abundant in lithium. The rest of it is lithium-7. So you have to use the more expensive one, but still, it's not that terribly expensive. You can produce lithium-6 by irradiating it with neutrons. You can produce tritium from lithium-6 by irradiating it with neutrons. And the cost of it is 30,000 grams of tritium. Okay. But there is even a better way. These chemists, they're really smart people.
Oh, some of them.
So the trick is to put the two together. Put the lithium-6 together with deuterium and make it lithium deuteride. Okay? And the way that it works is that when a lithium atom is hit by a neutron, it produces the tritium. And then the tritium will react with the deuterium and produce the neutron again. And then that circles, and it avoids the step of making tritium alone, because just having the lithium present, it immediately recirculates the tritium. I don't know if I'm explaining this properly. If you have a pellet, and it is a solid, a pellet of lithium deuteride is a small thing like that. If you heat that up to the right temperatures, then neutrons will decompose the lithium, will form tritium, tritium will react with deuterium and produce that 17 MeV of energy that we said before. So the net reaction really is deuterium plus lithium gives two atoms of helium, an enormous amount of energy. The bottom line here is that all you need for a hydrogen bomb is a pellet of lithium deuteride. Okay? And well, all right, so we can do that, and it's not difficult to do. So now we have a pellet of lithium deuteride. All we need now is 100 million degrees.
Have you been outside?
Yes.
Almost. So how do we do that? This time the physicists. By the way, this is the calculation of how much do we need. The Tomahawk cruise missile uses about 3 kilograms. That's a little bit bigger of lithium deuteride. And the first test done of hydrogen bomb in the Bikini Atoll, I think it was,
And we
1954, it used 400 kilograms of lithium deuteride. But even then, the cost was less than $1 million. So how do you do this? How do you get 100 million degrees in your kitchen or garage? Simple. You blow up a nuclear bomb.
In your garage.
So what you do is you put your fusionable material here. That is the lithium deuteride. And above it, you put a nuclear bomb, a fission bomb. Like, for example, the plutonium-239. And you blow up the bomb, the plutonium-239, the usual way. That produces 100 million degrees of centigrade, and that causes the fusion of lithium and deuterium into helium atoms, and it causes that enormous explosion. Here's the process of how that works. So it's simple, man. So we were able to make a nuclear bomb with uranium. We were able to make one with plutonium-239. And now it's just one small step. It's not that expensive either to make a hydrogen bomb. So, oops. So these are some of the hydrogen bombs that have been exploded. Well, these two down here, that's the Trinity, that was the test bomb in New Mexico. That's Hiroshima. And you can tell the size of it, okay? 15 kilotons. The plutonium bomb, the Nagasaki, is not here. That was 20. That was about this big. Mike, let's see, no. Yeah. Mike was the first hydrogen bomb. And this is 10 megatons. MT, notice this is KT, kilotons. This is MT. So the first bomb, this is deuterium bomb, the one that I mentioned that they used only deuterium. That produced 10 megatons. And then Bravo was the one that used lithium deuteride, and that produced 15 megatons. In fact, the scientists were surprised. They did not expect that much energy to be produced in this explosion. But then the Russians bested us all with the Tsar bomba, and that produced 50 megatons of energy. And so, hey, if they could do it, you can do it. So, thank you very much.
We want a neutron bomb.
Neutron bomb is a silent bomb. A neutron bomb really is a dirty bomb. By the way, the dirty bomb is an accumulation of radioactive materials put together and blown up into dust. And that dust is radioactive, and that is what is nasty about it. That's a dirty bomb. A neutron bomb would mainly produce neutrons. Now, neutrons are not good for you. The radiation of neutrons is damaging, as you see. They transform stuff. They destroy tissue.
So it's a clean bomb. A clean bomb.
A clean bomb? I don't know if there is a clean.
I heard that expression.
Yeah.
Maybe, yeah, opposite, dirty.
So what is a clean bomb?
one that's not dirty.
Yeah, opposite is dirty,
We
yeah.
don't know.
Do you know what kind of bombs that they're using in Nevada that they exploded in the sixties, seventies?
Well, they were testing the hydrogen bombs.
Hydrogen bomb?
Yes, they were testing the hydrogen bombs and mainly, well, at the beginning it was open. And then it was underground. But that is what they were testing, yeah.
So in the movie Oppenheimer, they did the first ones you were talking about, but then he was very conflicted about the hydrogen bomb because he knew it was gonna be so deadly.
Yes, but the problem, of course, was that the science was out there.
Yeah,
And
They knew they could do
so it would have been impossible to hide the science. And the thing is that if you didn't do it,
somebody else.
somebody else would do it because the science was there. And the Russians at that time, they had very, very good scientists. So now I forget the name of the Russian who developed their new hydrogen bomb. Sakharov. Anyway, so they had very good scientists, and so it would have been a very big risk not to develop one of those things.
Very good presentation.
I have an oral history note. My father was a nuclear chemist. And he was a junior scientist at Lawrence Livermore when they blew up the first atomic bomb, 1952, in Weetah Atoll. And only after he retired from his government work did he tell us that they were on the ship, the observing ship. And because the radiation was so much greater than they had calculated, they were all in crash positions, goggles on, eyes closed. But he said, at one point, I could still see the bones in my legs.
Wow.
Now,
Did it impact him down the road?
he lived to 80. He had Parkinson's. He had several forms of cancer. I was conceived after he was irradiated.
A glowing.
Just ask my wife.
But the clean bomb, just have to look it up. It's a bomb, a nuclear weapon designed to produce minimal residual radioactive fallout upon detonation.
Hallelujah.
It's called clean bomb. The other question was about Chernobyl. You talk about nuclear plants. So what, I mean.
Well, Chernobyl is a different thing. That's a nuclear reactor.
Mhm.
And so it has nothing to do with bombs.
We're done.
What happened there is that they missed the control. I showed you that there is a control of bars. And somehow, I don't know how it worked, but something went wrong with that control. And so they could not lower it and so the production of neutrons became too high. And that produced increase in temperature of the water and an increase in temperature of everything else. Things melted because of the energy produced by the neutrons.
The new nuclear plants here in the United States are being developed, nuclear plants. And we have,
Well, not commercially that I know. There is research into new types of nuclear reactors to produce energy. You see, energy uses the uranium-238, and it contains, well, the original 0.72% of U-235, or a little bit better than that, a little bit 3% of uranium-235. Okay, to make it stronger, to make it work better. What was I saying?
About
the
reactors.
United States.
Oh, about the new types of nuclear reactors. So they're working, I really don't know enough about it, but they have new designs of nuclear reactors. There are smaller ones. And I think that it will come back one of these days.
What to do about the waste? Is that a problem? How to get rid of the waste,
yeah.
nuclear waste?
Yeah, well, that is still a problem, and You see, ever since they started working with the nuclear reactors, they immediately realized that they will be waste. And that we have to get rid of the waste. So they started out thinking about it, and in fact, there are two projects to bury the waste. One is in Arizona, it's called Yucca Mountain, YUCCA, Yucca Mountain. And that is finished. It is an enormous complex of tunnels. And the process is pretty clean as far as I understand it, because they would take the nuclear waste and would vitrify it, okay? Vitrify it means that they will put it, encase it in glass. And it will be sort of big cylinders of glass that will contain this material. In other words, it will be very difficult to leach out the nuclear material, the radioactive material. And it is these cylinders that would be placed in holes inside the Yucca Mountain itself. And so everything is ready. Everything has been ready for 30 years, except for one thing, that Nevada doesn't want it.
Yeah.
Not in my background.
They would lie, yeah.
It's been proven that it will take 100,000 years for it to fail. Not enough.
But in France, for example, I understand they have most of the energy comes from nuclear plants.
Well, yes, because they have a lot of nuclear plants. In fact, 70%, I think, of their energy is nuclear. So I don't know what they do with their waste.
That's why they recycle.
One idea was to throw it in the ocean. That's not a good idea.
No, that's-
But it was,
What is the latest as far as possibilities of fusion reactors? And what is the latest in cold fusion, so-called cold fusion?
which reactors? Juicer?
Fusion reactors.
Oh, fusion reactor. Well, the last I know is that it will take 10 years to develop the fusion reactor, and it always will take 10 years to develop it. I know there are 40 different companies in the world that are trying to break through. And they have made some significant breakthroughs, like passing the how do you call that, Mark? They produce more energy than they consume, but it is still very far away from being commercial. And the last that I read about it is that it takes X number of years to develop it. It's just not a simple thing. But fusion reactors, of course, they don't produce this garbage, this radioactive material. And so it will be perfect. They are the solution. So I guess that's why there are so many people working on it. They spend billions of dollars
You should
in
see,
trying to get it.
I used to work on a nuclear plant.
Yeah,
And yeah, and to see the spent fuel pool. It's beautiful. It's crazy. It's beautiful. It's just the most beautiful blue color, and you've got all these things in there, and you're way up high, and
there's a name for that effect. What is it? Markovsky effect?
you just want to dive in. I mean, it's just beautiful.
No,
It's great. But yeah, they did a lot of, they do a lot of health things. And before you even set foot inside, you have to take a lot of training as a worker on health physics and your radiation rates that you're allowed to get. And through each door, you're looking through things and measuring, and they're checking you and all that kind of stuff.
Where was this?
I worked at Turkey Point nuclear plant down in Homestead, and I also worked at
It's here.
in Florida Power and Light, and the St. Lucie nuclear power plant on Hutchinson Island near Jupiter.
Well, there's still energy in the waste. Is there a lot of work in trying to capture that energy that's left in the waste?
Good question.
The waves? Yeah, they're talking about it. They don't have a good technology. They have tests and it's good, but somehow it's just not good enough.
Should we all expect a visit from the FBI now that we've?
We've all got our phones on, they know.
Presentation. All of this is on the internet. All of it.
No, it's a quick
And
presentation.
the key is how far along in the Iranian. That's,
Well, the Iranians are, they say that their enrichment was up to 60%. And so now they have to take it, in order to make a bomb, they have to take it to 90%. Now, my view is that all this talk about the danger of Iranian and nuclear bomb is just garbage. Because for a number of reasons. Number one, they have not been interested in doing it. They have shown that. It will take them 10 years to go from the 60% to a bomb like the ones we saw. And besides, recently it has been shown that they have something that is more valuable than a bomb. And that is the potential of destroying their neighbors. And just by, that deterrent is sort of, for me, equivalent to having a nuclear bomb. They don't need a bomb to throw somewhere else.
We're going to get it Israel through oil. I think that's their.
Your map of countries with the bomb, there's one that no longer has the bomb. It was not shown as having on your map, but that's South Africa.
Well, I never did that.
I don't know, one of my business partners in South Africa was the chairman of the nuclear decommissioning, so
The commissioning of the project,
could be, yeah, I don't know if they had a bomb or not.
maybe they.
I
had
would
a
guess
secret
that they
bomb,
did.
I don't know, but officially they didn't have it. Neither did Libya.
Mm.
Very good presentation.
So how many people remember, what's his name? Lair, who did the song, who's next?
Who's next?
Yeah, we got the bomb and that was good because we love peace and motherhood. Then Russia got the bomb, but that's okay because the balance of power is maintained that way.
Remember it?
And then I can't remember the whole thing. Egypt got the bomb.
Since I got it, I was thinking about that.